Today we'll be covering searching and sorting. This is a pretty interesting topic actually because it allows us to do like a lot more things than we've been able to do. It may be a little complicated because this isn't regularly covered in intro like Java classes, but it's based on everything that we've already learned, like loops, arrays. We've already practiced all of those. So searching and sorting is just taking those to like the next level. And I think it shouldn't be too bad. But we'll see how it goes. Alright, let's go on. So, first off, when we're either searching or sorting, well, searching in this case because I put that on the slide, but when we're doing either of those two, we'll be using an array. An array is like what we'll be accessing and manipulating every time we're searching and sorting because that's like the most commonly used data type for this. So say you have an array that has 5 elements like this. How would you sort it by a specific number? Or how would you find a specific number? And this process is called searching because you have to try to like identify where it is in the array, right? That's something that you do like in your daily life as well. You always search for things when you want to be able to like use them, right? So it's the same thing in CS. Computers will also need to search data, but they don't know where each value always is. So unlike us who are able to like see where the data is and like just immediately identify like, oh yeah, there's a 3 in this spot. Computers, they're not able to see that. What they see is like the memory address. So they need to use these searching algorithms to efficiently find ways to locate those data values, right? So they don't see the values like us. They see the memory addresses. But they can access those values and find out like, is this value equal to the value that we're searching for? That's something that they can do. So yeah, there's a bit of a discrepancy there that we should highlight. So what are the common searching algorithms? Well, in AP-CSA, so some of you might have gotten your AP scores back today. Hopefully those went good for you. But in AP-CSA, that's computer science class for AP, you learn linear search and binary search. So linear search, we'll be covering like what that is, and binary search is it's more efficient than linear search. Also it sounds cool, so we'll see how those work. So linear search, I put a visual here to show how it works. So we start from the first element, right? Then we check, is it equal to a certain value? So we're checking, is it equal to 33 in this case? So we start from the first element. If it's equal to 33, then we return that value. We return the index. Otherwise, if it's not, we increment and go to the next index value. So is 10 equal to 33? No, it's not. So then we go to 14. Is that equal to 33? No, it's not. So we continue on, and we do this until we get to the value of 33. So this is pretty useful like in simple cases when we have like a small array like this, but this may not always be useful. But we'll see like how we can actually implement this next. So one thing to know here is that this array, it seems like it can be in any order because we'll always either get to the value at some point if given the value is present in the array. So if we know that it's present in the array, then we'll always get to that value, even if it's like not sorted like this. If it was sorted like 1, 2, 3 all the way to 33, then we would still get to the value. And there's a difference that we'll see in binary search in how like binary search works. So yeah, that's linear search. Here's like the steps that we covered. So start looking from the beginning of the array, right? Is that current value equal to the target? Well, what is the target? Target is the value that we are trying to find. So in this case, it's 33 because that's the target value that we want to know. So is the current value equal to the target? Current value is the value that we are looking at, right? So 10, 14, 19, 26, whatever this whatever is currently in the array. If that current value is equal to the target, then we go on to step 3, which is to return or process the value as needed, so do whatever we want with it. But if the current value is not equal to the target, then go to the next index and repeat step 2. So step 2 is this current step. Next index means we just go to the next value. So that happens whenever we see this like red square, and then when we see the green square, that means we found the value. So yeah, that's linear search. Fairly simple. It's like just start from the beginning and search the array elements. So here is the code implementation. So I defined a class called linear search, and then I made a private field variable called myArray. And then in the constructor, remember that's like the initial state of the class, that's where we initialize this array with these elements, right? Single digits like 6, 3, 8, 4, 5, 9, and so on. Then we have our search method. This is where we implement the algorithm. So we have a parameter called target, which is the value that we want to find, right? So it was 33 here. So that will be our target. That's going to be the value we want to find. And then for every value in this array, so we start with an incrementer called I, and then we increment that until we get to array.length, which is 9 in this case. Yeah, 9. And then we increment I after we evaluate this if statement. So if my array at that index is equal to target, then we return I. So that's analogous to this step 2 right here. Then we return I, otherwise we'll return 1 at the end. So notice how we have like a return in this if statement, and we don't have like any else right here. So we don't put this else in the for loop, because if this if statement evaluates the false, and we're still looking at the first value, which is not 33, if the if statement evaluates the false, which it will in this case, then it's just going to return -1. And we don't want to do that, right? We want to return -1 only if we've searched through all the elements and if the target element is not present in the array. So that's why we do it at the end. And -1, we use -1 because that tells us that it's not existent in the array. That's just like a common thing in CS. So yeah, there's this method in Java called indexOf, like string.indexOf, and that will also return -1 if a like certain character or string is not found within some other string. So yeah, that's how we implemented the search method, which will implement linear search, and then in the main method we just find the value 3. So this is something that is like kind of done in MontaVista. Like you would have a program structure like this in the beginning, in the introductory to Java class. So in the main method, you wouldn't write your code. You would just create an object, and then you would run a method with that object. Like you don't implement all of this code in the main method in MontaVista. So yeah, if you're going there for next year, then just keep that in mind. Most of your code will not be in the main method. It's just going to be sectioned off like this. So yeah, here is the search method. I just put it there for like clarity, I guess. But yeah, key thing to know is that we search through all of the elements in the array. If it's not equal to that element, then we increment it, and then if it is, then we find it and we return it. And yeah, know the discrepancy between putting the else inside and then returning, and simply just returning outside of the for loop. So yeah, those are two important things for linear search. So for binary search, let's say we have this example right here, and we want to search for 41 in this array. So what we do here is, first we see how many elements are in this array. So it seems like there's 11, and our maximum index then would be 10, right? because the max index is the number of elements minus 1, so we have 10 as a max index. So then we have to divide that by 2, so we do 0 plus 10 and then divide it by 2, and then that gives us 5. So that's the middle value for this array. It's 28. So we have to find the middle value first. Then we check whether this target value, the value that we're trying to find, is greater than or less than this middle value. If it's greater than, then we search this side of the array. If it's less than, then we search this side of the array. And you may already be able to tell, like, we need the array to be sorted, because if it's not sorted, and we assume that we need to search the right side of the array for any values that are greater, then we're not going to get our desired output, right? We're not going to be able to find the value because the array wasn't sorted. So yeah, we have to be sure that the array is sorted before we perform binary search. So anyways, if 41 is greater than 28, then search this side of the array, otherwise search this side of the array. So since it's greater than 28, then we search this side. Then we do the same thing. So 6 plus 10, that's 16, right? So we have to add the minimum and the maximum indices, and then we divide by 2 to find the average, or the middle value. So 6 plus 10, that's 16 divided by 2, that's 8. So next up we check 67 as the middle value. So is 41 greater than or less than 67? Well, it's less than, so we search the left side of that. Left side of this part of the array, right? Let me just wait for it. So we search this part. So then we do 6 plus 7, and then we divide that by 2, so 13 divided by 2. I mean, I don't think this example is entirely correct, but let's just say we got 7, so we're checking 7. In reality, we would be checking 6 because in Java, the division for integers always truncates the decimal. So 13 divided by 2 would be 6 in Java. In real life, it would be 6.5, but we removed the 0.5, right? So we check 6, and then we see that 6 at index 6, it's equal to 41, and then we return it. But if we rounded the 6.5 up to 7, then we would check 7. We would see that 41 is less than that, so we check this side of the array. Then we create a new array, and then we check that. And it's 41. So yeah, that's how binary search works. Here are the steps. There's a lot of text on this slide, so let's break it down. So, steps for binary search: array must be sorted. That's the precondition. So a precondition is like your, it's like what you need before you execute some steps. So, start with the middle element of the sorted array. Remember, to find this, you can divide the minimum and maximum indices by 2. Is the middle element equal to the target? If so, then go to step 6. So that means we already found the value. Is the target less than the middle element? Well, then we wait, there's a question in chat. So should the array be sorted from least to greatest or greatest to least? Good question. So in the case of binary search, we would sort it from least to greatest. Yeah, hope that answers the question. The reason why we do it from least to greatest is because that's like kind of intuitive when we're dealing with the arrays. So yeah, we do it from least to greatest. The third step is the target less than the middle element? So if the target is less than the middle element, then that means it's less than the value at the middle element, right? So it's kind of like we go to the left half of the array. So it's like a number line basically, right? Because a number line, the smaller values are on the left and then the larger values are on the right. So we go to the left half of the array if the target is smaller than the middle element, and then we repeat steps 1 to 2 on the left half of the array. Then we go back to the middle element, and then we do the same steps. If the target is greater than the middle element, then we do steps 1 to 2 on the right half of the array. So we go back and then we do it on the right half, like that. And then we repeat this process until the target is found or the subarray size is 0. And then we return or process the value as needed, as we did with linear search. So why is this more efficient than linear search? Because we do a lot less of these comparisons. So when you're doing like comparisons in on like hardware, it takes some energy, right? So you want to like be able to minimize that. So when you saw with linear search, we were comparing with every single value in the array, right? We're comparing with 10, 14, 19, and then all the way until we find this correct value, until we find the target. So the worst case, we would have to look through the entire array, and our target value would be at the end. So there's something that you can use to like represent this. It's called like big O notation. I don't know if some of you have heard it before, but it tells you like the complexity of an algorithm and like how it would evaluate in like the long run. So well, that's like beyond the scope of what we're doing right now, but if you do know about that, that's like something interesting that you can delve into. But anyways, generally with binary search you would have like less comparisons. Alright, another question. If the target is the same number as the middle element, then we would just return our processed value. Yeah, that's correct. If the target is this value, then you would just return that. So that's why we have a step to check is the middle element equal to the target. Then we can like directly skip all of these. So yeah. So here's the code implementation. In the main method, so here I did it a little bit differently compared to this linear search. Here I just wrote some code directly in the main method, but if you're taking the class at Monte Vista, you wouldn't like do this. But anyways, so in the main method, we make an array called 2, 3, 4, 10, 40. It has the name of array, ARR, however you want to say that. And then our target is 10, so that's the value that we're trying to find. That's not the index, remember, this is the actual like value that we want from the array. And we're trying to find the index of that. So we're going to do this binary search. We're going to call the method with this array argument and then this target argument. So these parameters are initialized for these values right here. So we make a left variable. That left variable is going to be this value right here. It's going to be the beginning of the array, because we're going to search through the entire array starting from this point for the value, right? And then the right index is going to be array.length minus 1, right? We know that the last index is the length of the array minus 1, because here we have 11 values and our index is going to be 10. So that's our right value. So we're searching from left to right. So while left is less than or equal to right, we'll see why we're doing that. Then we calculate the middle value, right? So this is one way you can do it. You can say left plus right minus left divided by 2. You can also just say right plus left divided by 2 as we did before, but they'll be the same thing. So you find the middle value. If the middle element is equal to the target, which is our step 2, then we return the middle value, right? So we're completely finished with this loop. If you return inside a loop like this, then it's going to stop executing this method. So yeah, if we found the value, then we just return the index. If the array at the middle value, at the middle index, is less than target, then we if the target is greater than this middle value, then we're going to have to search the right side of the array, right? So we say left equals mid plus 1, otherwise right equals mid minus 1. So that's how we actually like section off the parts of the array like this. So after we do that, we're going to go up here again, and then we're going to check if left is less than or equal to right. And then we're going to repeat the same process, but this time, since left is different and right is also different, we're going to be checking different bounds for the array, or like a different like section of the array. So after we finish this loop, we're not going to have return the value, right? Because this is never going to have run. That means that we weren't able to find the value. Oh, there is a question in the chat. Can we also search from right to left, or is it only from left to right? So the searching that you're doing, it's not necessarily from right to left or left to right. It's like you find a value and then you check whether it's greater than or less than, your target is greater than or less than or equal to that value. If it is, then you check like the left side, or if it isn't, then you check the right side. So it kind of depends on how you're doing it. It's not necessarily like linear search where you're going from left to right, but yeah, you can, it's a bit different. Yeah. For linear search, you could also search from the end of the array, and then go to the beginning. It doesn't really matter, but yeah, I just chose this example here because it was fairly simple. So anyways, there's that. So we check while left is less than or equal to right, because if left is greater than right, then that means that the index here on this side is going to be past the index on that side. That means we've incremented it beyond like a certain point. And if you have something like that, right, if the left is on the right side of the right, I don't know if that makes sense, but if like the left index is somewhere over here and the right index is over here, then that means that you've looped through so many times that you've incremented or decremented one of those values, and you weren't able to find the element, the target, right? So then you return -1 because you didn't find the index. So yeah, that's binary search. Let me think if there was anything else that I needed to explain. I think we covered pretty much everything about this, so we're good. So what did we cover? Well, linear search and binary search, right? So linear search, we saw that it was an easy way to look for something, not the most efficient, and it works for any type of array, right? We can go from, let me go back. So we can go from right to left, or we can go from left to right, and it doesn't matter if this array is sorted, because given that the value is already in here, we're always going to be able to find it. So that's linear search. It's pretty simple to implement, right? We saw that it was only one for loop. Binary search, it's also pretty, well, it's not as simple as linear search, but it's efficient, which is what matters in the long run. So it's an efficient way, but a little more complex than linear search. It's faster than linear search, and the array must be sorted. So that's the precondition that you need. So next up we have sorting, right? So we have 3 algorithms that we're going to cover. We have bubble sort, insertion sort, and merge sort. So these 3 are these 3 are the ones that you do in CSA, I think, APCSA. There's also selection sort, but I didn't put that on here just for like time. So yeah, so bubble sort, insertion sort, merge sort. We'll see how those work. So bubble sort, well, it's fairly simple. This is the most simple of the sorting algorithms. So what you do, let me wait for this to actually restart. So there we go. So you compare 2 values at a time. You compare here, well, we're doing like 7 and 1, and we find out which one of the values is greater. Whichever one is greater, we try to move that to the right side, and then we'll end up with the greatest element at the end of the array for each iteration. So you're gonna like probably realize that we have to do this several times, because each time we're going to move one value to the end of the array, and that value is going to be our greatest value in that iteration. So here we saw that 8 is the greatest value. Next, on the next iteration, we're going to move up 7 all the way up here. So, well, I mean 7 is already moved up, but in the next iteration, 7 will be at the end. On the first iteration, which is this one, 8 is at the end. So yeah, maybe I could have chosen a better example, but we're at least able to see how it's like comparing these two values. So yeah. So for this algorithm, you need two loops. So I made a sort method here inside this bubble sort class. In the outer loop, we're gonna loop through 0 to nums.length, which is the length of the array. So we're gonna move all of these elements to their correct position, and we have 6 elements here, and 6 is the length of the array. So you can kind of think of it like that. We need to move all of the elements, so we need to move it for like the nums.length amount of times. Alright, so for the inside loop, for each of those iterations, what we're doing is we repeat swapping until a certain amount. So on the first iteration, this is kind of like specific to this implementation, but we will repeat this swapping, or we'll check if we need to swap it until the second last value. So I mean, if that may not be like very clear, but let's see how it works in here. So on each iteration, I put it right here on the right side. So on the first one, we move 5 into the rightmost position, then we move 4 into the position after that, or the one before that rather, and then we move 3, then we move 2, and then 1 is already here, so the last one and the second to last iteration are the same. So we're going to be repeating this for like every value that we have. So if the current value is bigger than the next, then we swap it. So we're accessing the current value with j, and then we go through and we check all of these values until the last one. So let's see what happens here. In the first iteration, we check all of these values, right? Because nums.length is going to be 5, I is going to be 0, and then 1 is going to be, or minus 1 is going to make this 4. So 0, 1, 2, 3, 4. And then as we move more elements into this array, I is going to increase, right? So we subtract I because we assume that this part of the array is already sorted. So we're going to check these elements, then we're going to check these elements, then we're going to check these, then we're going to check these, and then we'll check the last one at the end. So the next one is insertion sort. So this one is a bit more easier to understand, in my opinion. So what we do, let me wait for this. So we're on the 4th round. Alright, so now we're on the first round. So we start at the second element and we assume that the first element is already sorted. Then we move the first element into the positions that would be like respective to the first element. So let me see if I can get this. So we see here we have a 2, and then when we compare that to the 3, 2 is going to be less than 3, right? So we need to move it before 3. Then we cover well, I have to wait for this. And then we cover the next element, which is going to be 8. So since 8 is greater than 3, we keep it in this position. Then we cover 1, since 1 is greater than, or it's less than all of these values. We move all of them to that side, and then we put it in 1 in the first position. Then we move 5 to this position right here. So it's kind of like we're building the sorted array from the left-hand side instead of the right-hand side, as we did with bubble sort. And the reason why this is going to be more efficient than bubble sort, because like before, like we don't have as many comparisons as we do with bubble sort. So here is the implementation for bubble sort, or insertion sort, sorry. So we're going to have one outside loop that's going to insert numbers before or after the first element. So we'll start from index 1, which is the second element. We start from here. So we say I equals 1, and then I is less than the length of the array. Then we copy each current value from the iteration to a new variable, so we know what the current value is. And then we have the position before our current value. So it's going to be the 0th position in this case, and then we need to compare that. So we'll walk back, meaning like we'll compare each of these values. So like 1 we compare to 8, then we compare to 3, then we compare to 2. So that's what we're doing in this. We'll walk back until we reach the 0th index, or we reach a value that's less than or equal to our current value. So that's what we saw with the 1 in here. In this case, since it was less than 8, 3, and 2, we had to move it to the 0th position, because that's like the first position that we can move it to. So while j is greater than or equal to 0, and the value that we are at is greater than the current value, then we want to move the current value back. And then once we find it, then we insert the value, and then we continue walking back. So we're like moving back this element at this point. And then we move the temporary variable that we created earlier. So that's insertion sort. So for merge sort, which is fairly interesting, so what we have here, we're like splitting up this array, right? You can see that we're breaking up this array. That's called splitting, and then we merge it by sorting each of the smaller arrays. So we have 1, 3, then we're going to have 7, 8, and then 2 and 4 for the last one. So now we have 4 arrays of 2 elements, as we see here. And then we merge these 2 arrays. So we compare the values. We get 1, 3, 5, 6 because we merged those 2 arrays. And then for this one, well, we know we're going to get 2, 4, 7, 8. And then we're going to merge this one and this one. So this is like divide and conquer, because we're like splitting up the values, the arrays. And you can see that this is going to be implemented, or it can be implemented recursively, because we're like repeating this like splitting and merging of arrays, and that's something that's really efficient to do recursively. So the implementation for this is a bit long, so I couldn't like fit it on one slide, so I just skipped the implementation for now. But now we'll do the type along, which is implement binary search in a recursive format. And yes, you can implement this recursively. So remember, binary search was our searching algorithm that allowed us to find the value pretty efficiently, like more efficient than linear search. And you can think of this as a recursive algorithm, because it's similar to like merge sort in a way. Like we're splitting up the array, but the only thing we're changing with each iteration is like the indices that we are currently like accessing the array at. So with each call of the recursive function, you should change the indices that we're looking at, but you can keep the array the same because you want to access those indices for the same array. So as a hint, you would have the parameters of array, then you would have your target because that's what you're searching for, and then you would also have left and right for each parameter. So yeah, that's like a small hint that you can use. Let me see how much... Oh, that was the answer. Well, let me see how much time we have, and then let me like give you some time to work on this based on that. So actually the implementation for binary search is going to be like pretty similar to the implementation in recursive format is going to be pretty similar to our like looping format. So I'll put that on the screen actually so that you can look at it. So this was our binary search thing. So since we have some time, I'll give you guys, let's say 7 to 10 minutes. Let's say like 9 minutes to work on this. So I'll give you guys 9 minutes. Try to see what you can do with this, and then I'll come back and let's discuss the answer after that. So yeah, 9 minutes, and then try this out. And the prompt was just to like implement this in recursive. Alright, so 9 minutes has gone by. Let's review how this recursive algorithm actually works for binary search. So let me share my code window because we need to see that. Alright, so this was our type along folder from last time, right? We had our Fibonacci and exponential programs. So let's go on to number 9, which is our 9th folder. So we can just call this binary search recursive.java. Let's zoom in. So the prompt was to implement binary search in a recursive format, right? So yeah, I'll just put that right there. So we can define a, hold on 1 second, let me make sure that recording is good. Alright. Okay, so for our method, right, we know how, let me actually get the previous binary search so we can like compare. So this was our previous binary search, right? We had our 2 parameters, and then we had the logic right here. So instead of writing a loop this time, we're going to pretend like our function is going to get called with every loop. So we're not going to define like an overall loop in our program, but we can just use recursion to our advantage in that way. So binary search is going to be our method name, and then by like Java convention, we are allowed to have like the same method name, but we need to change the parameters. So let me copy and paste these two. So these are our 2 parameters, but we're also going to have an int right. Let's do left, and then int right, like that. So we have 2 integers for the left and right indices, right? So instead of writing this for loop, we can just go directly to an if statement. So we can say if left is greater than or equal to right. So it's going to be like the same, but we're pretending like each time we call this method, it's going to go through an iteration of like this loop. So if left is greater than or equal to right, wait, hold on. It should be the other way. If left is less than or equal to right, then we need to create our mid variable, right? That's going to be our middle index that we're checking with the target value. So right plus left divided by 2. So now we have the element that we're comparing to our target. So now we need to compare it to our target. So if the value at the middle index is equal to target, then we can just return mid, right? And that's going to like go up the recursive stack and like finish all of those iterations that we were doing before, all of the method calls. Otherwise, if target is less than our middle element, And this is like the same code as last time, basically. If target is less than the middle element, then we can call binary search with the same array, same target, except we need to specify a left and a right. So let's think about this. If the target is less than, if the target is less than the middle value, then we need to check the right side of the array. Wait, let me think about that. No, we would check the left side of the array because the target is less than the middle value, right? If we had an array 1, 2, 3, 4, 5, 6, 7, like remember it needs to be sorted, so I'm doing this. And if we're searching for 2 and 2 was less than 4, then we would need to check the left side. So that's what we're doing here. So to check the left side, we would go from left, because our left index is the same, but we would go to mid minus 1 as the value of our right. And we need to return this value. So we're going to call the same method again, but we're using like the recursive method, or rather recursive algorithm. Otherwise, we know we need to check the right side of the array, right? So it's going to be like the same now. So we have our array, we have the target, then we have, this time it's going to be mid plus 1, because we go, this is our mid, and then plus 1 is going to be 5. So 5 to 7, that's going to be mid plus 1 to right. Oops. Yeah, mid plus 1 to right. Now if we were not able to find the value, right, then we need to return -1 after all of this. And it's going to stop giving us that error from before. So that is our recursive method for binary search. Let's see how similar it is to the first one. So instead of initializing the left and the right, we just assume that the user gives us to them like directly. And then instead of having like a while loop right here, we're pretending like we're gonna loop through this algorithm inside of our like stack, and then with each call it's like an iteration of this loop, right? So then we can define the inside of the loop like similarly as we did, and then we can also write the -1 on the outside. So yeah, the structure is very similar. So in this case you could use like either loops or recursion to implement binary search. Personally, like I would prefer recursion just because like I like the simplicity of it, but it doesn't really matter in this case because they're so similar. So yeah, that was our binary search. Let's see the next type along. Alright, so this was our code implementation for loops, and then let's go forward. This was our recursive method, and then this is our second type along. So imagine you have a group of people standing in line, each with their height randomly ordered. Alright, so it's like a random array. So bubble sort works by comparing adjacent people and swapping their positions if they're out of order. Shorter people before taller people. Shorter person before taller person. This process repeats until everyone is arranged by height in increasing order. So create a height array and initialize it with heights 175, 160, 185, 170, 155, and these are in centimeters. And then use bubble sort to sort the heights. Print the array before and after you're done sorting. So I'll put the bubble sort algorithm. Actually, I'll leave this right here. Well, hold on. Maybe let me just put the algorithm actually, because you might not remember how to do it. So I'll put this algorithm, try this on your own, like see what you can get done in like around 2 minutes, and then I'll come back and then we'll look at the solution. Alright, let me unpause the recording. So yeah, let's work on implementing this. So in this case we have these heights, so let me put this, let me just copy it for now, and then let me share my screen for the code window. So yeah, this is the window that you're able to see right now. So we have our binary search recursive.java. I made a new program called height_sorter.java, and then I added a main method in it, so you can do that. So for this program, I'll do most of the work in the main method, so we can make an int array, and then initialize it with those same values. I'll put it in the chat so like you can copy it. Okay, so I put the values in the chat. So to implement bubble sort, what we need to do first is create the outer loop, right? This loop is going to loop through all of the elements in the array. So we're going to say for int I equals 0, I is less than nums.length, and then we increment I. So there's a few ways to do bubble sort, and yeah, I changed the array name just now. There's a few ways to do bubble sort. For in this case, we'll just do it like how we had it on the slides for simplicity. So we'll loop through in the outer array for each element. So we're gonna loop through 5 times, but we're not accessing each element each time. We're gonna like run a different loop. So we're gonna say int j equals 0, and then j is less than nums or array.length, and then we can say j++, and we can say -1 because we're gonna have to loop through this we're gonna have to like access the elements for each like sorting this many amount of times, so 4 times in this case. So then we can program the swap. So if the current element, which is nums at j, is greater than nums at j+1, I don't know why I keep using nums, I should use array like that. So if the current element is greater than the next element, and this is also another reason why we use -1 here, because when we're checking this element and the next element after that, we want to make sure that we don't get an index out of bounds error. So that's why we use -1. Because if we said j+1 and our index was 4, then it would try to access index 5, which is not like available in this array. So if the current element is greater than the next one, then we need to swap them. So we can do the swap like this. We can create a temp variable and set it to j, our current value, and then we can say our current value is equal to the next value, like j+1 like this. And then we can set array of j+1, the index at j+1, equal to 10. So effectively, we've swapped these two values. So let's see what the prompt was asking actually. So it asks us to print the array before and after. So let me put that right here. So you can see here, print array before and after you are done sorting. So let's do that. Before, we can print it like this. We can say for int x in array. So this is another way you can write for loops. You can say for every integer in this array, then you can just print it out. Print x plus a space, like that. And you don't really need these, but you can keep them there. This is our array before, and then this will be our array after. So it's the same printing statement. So let's run this and see what we get. Okay, well, I have a bunch of errors from my other programs. So let's just run it in terminal. Alright, clear. So let's navigate to our 9th folder, and then let's do javac height sorted.java, and then run that. And then you can see we have, well, I should have done it like this. I should have said print without the ln, and then I can say print line, like after, and then print without the ln again. So let me try running it again. So yeah, before we have our non-sorted array, and after we have our sorted array, like this. So yeah, that was our type along for this program. I'll be sending out the code and the recording as well after. In the meantime, let's go back to the slides and then see if we have anything else. Alright, so we don't have anything else. So we've covered searching and sorting this class. So if you do want to support me, like I said before, like you can donate using my Zelle ID, which is my email, crochet.db@gmail.com, or you can also like my YouTube videos and comment. But yeah, you guys are free to go. Thanks for joining these classes, everyone. I hope you learned something new. If you did, then you did pretty well, and you accomplished like the goal of what I was trying to like get out. So yeah, good job, everyone. Hopefully you like continue to practice Java and other CS related stuff, because it's pretty interesting. If you don't, like, continue learning, it's cool to learn. Other than that, I don't really have much else to say, so you guys are free to go, and thank you. I'll stay after like for 5 more minutes, probably until like 3:10 to answer some questions.